Greetings and welcome to the Chemistry 223 lecture for Chapter 16, which I have called Chemical Thermodynamics. This is a fascinating chapter in my world. This is going to revisit the ideas of enthalpy, which is like exothermic and endothermic reactions. And in the past, up until this point, we've basically assumed that reactions which were exothermic are the reactions that occur. But we're going to see that it really isn't just up to enthalpy. It's actually up to entropy. And you can see in the little graphic right there, which I love, this is basically an office that represents entropy. And you can see how the door is off the hinge and there's a hole in the floor and the lamp isn't connected and the garbage can is filled over. Well, believe it or not, all of those represent what entropy is all about. And entropy is totally fascinating. We're also going to look at something called Gibbs free energy, which is used to explain absolutely when reactions occur or not. So this is a powerful chapter. This brings a lot of the stuff we've looked at up and since Chem 221 up till now into one complete package. And when you couple this chapter with the next chapter, which is on electrochemistry, by the way, oh man, we've really got a pretty cool vision as to what chemistry can offer people. So without further ado, let's get into this material and get ready to have your mind blown sometimes. In chemistry, thermodynamics and kinetics are probably the two most important concepts of all. Thermodynamics, which is going to be the focus in this chapter, basically is trying to predict if a reaction can occur given enough time. And sometimes reactions do occur, and sometimes they're really difficult to get to occur, if they occur at all. This is thermodynamics. It's kind of like a thumbs up, thumbs down as to if a reaction will occur or not. But in the back of your mind, you also have to remember that kinetics, which is the study of time, is also really important to chemistry. Thermodynamics might give a reaction a thumbs up, i.e. a reaction that's going to occur, but it doesn't say how long it's going to occur. Some reactions, for example, diamond going to graphite, which is thermodynamically favored, those reactions at first might freak people out because, oh my gosh, I've got to go sell all my diamonds. They're going to go to graphite. And again, graphite's like in pencils. Diamonds, of course, worth a lot more money. But nobody should have to go sell all their diamonds, all right? The speed of the conversion of diamonds to graphites is incredibly slow. And your children's children will have your diamonds if you so wish to bequeath them down the road. It's nothing, diamonds aren't going to break down to graphite anytime soon. So when you're a chemist, you really should think about both the thermodynamics, if a reaction will occur or not, but also in the back of your mind, keep in mind that some reactions take longer and some reactions go faster. That's going to be the domain of kinetics, and those are two separate fields. This picture right here is kind of a flashback a little bit from Chem 222 when we talked about kinetics. This is a reaction diagram. It shows reactants on the left and products on the right. And reactants to products, that transition, that would be a question for thermodynamics. And you can see in this example, the products is at a higher energy than reactants. So this would be, if you will, an endothermic reaction, or at least you have to put energy into it and stuff. On the other hand, the hump in the middle, which is related, if you remember, to the energy of activation, that's where kinetics pops in. And as that hump gets higher and higher, then the reactions get slower and slower. Now, in kinetics in Chem 222, we only talked about enthalpy as reactants to products. But you'll see there that there's a term called spontaneity. Spontaneity is a different kind of thermodynamic quality, and we'll talk about that in this chapter right now. So in Chem 222, we only used enthalpy for talking about reactants to products, and we saw that some, like in this case, products were higher, so it was endothermic, but other times products were lower than reactants, and those were exothermic. We're going to see that it's actually more than just enthalpy, and that's what this chapter will be about. In this chapter, we will be visiting thermodynamics again, like we talked about, and we need to re-talk here a little bit about the first law of thermodynamics. And in Chem 221, which seems, I know, sometimes like a long time ago now, but anyway, we did talk about first law of thermodynamics, and this is really fundamental for all physical science. And first law says that energy cannot be created or destroyed, and this is the conservation of energy. So when you're making a product, you can't create energy and you can't destroy energy. Energy is transferred. And people talk about the energy of the universe, or the change in energy of the universe has to be equal to zero. So if you have a zero energy, then the energy has to come from or be distributed between the system and the surroundings. And usually energy is changed through heat and or work. And we talked about in Chem 221 how most of the time chemists are interested in the heat part, and that applies here too. And heat at constant pressure is where enthalpy comes from. So enthalpy is essentially a measure of heat. Energy is given off, it's exothermic. Energy is absorbed, it's endothermic, and stuff like that. Pretty cool. So anyway, this is a quick review of the first law of thermodynamics. Enthalpy is given the symbol delta H, and it's going to be important in this chapter. So I want to just go through again a little bit more of a review of how this all works. Again, if energy is given off, it's considered exothermic, and the value of delta H will be a negative number. So if you saw a number like minus 26.7 kilojoules per mole, like in the lower right, that would be an exothermic energy. On the other hand, if you have an endothermic energy, it's a positive delta H. So if you had, I don't know, positive 391 kilojoules per mole, I see for the NH bonds down there, that would be an endothermic transition. We talked in Chem 221 about Hess's law, which is when you can combine reactions together to give you an overall reaction. We also talked about how you can find the overall delta H of a reaction by taking the delta H of the products and subtracting the delta H of the reactants. We're going to do stuff like that in this chapter. So if that doesn't look familiar, I do recommend you look back in chapter 5 of Chem 221. That was something we did towards the end of the chapter, and that'll be really helpful to us. We also talked about in Chem 222 a way to find the energy through bond enthalpies. This table right here is one of them. It's bonds broken minus bonds formed. That's another way sometimes you can find the enthalpy of a reaction. So all of these are cool things to do. If they're not looking familiar to you, you might want to go back and review them, especially that delta H products minus delta H reactants. That's going to be something we'll use in this chapter and equivalent kind of ways. Thermodynamics asks if a reaction will occur. Like if you're ever curious, you mix two chemicals together, are they going to happen? All right, well, that's a great question, and that's trying to what thermodynamics is trying to offer. If the reaction does occur, the system is considered favored to react, and that's really what a product-favored system is. So now we're talking about Chem 223 stuff. Equilibrium constants that are greater than 1 are product-favored, and really all product-favored equilibrium constants are ones that are going to react. We call these spontaneous reactions, and I'm not really a big fan of the term spontaneous because to me spontaneous means instantaneous, like bam, I'm going to snap my fingers and all of a sudden it's there. But spontaneous in that context sounds more like time, like it happens instantly, and that's not what the scientific definition of spontaneous means. Spontaneous in a thermodynamic quality, which is what we're talking about here, means that the reaction will be product favored. You expect the products to occur. Most product-favored reactions are exothermic. They'll have negative delta H's. And until this chapter, that's what we've kind of assumed informally, all right? But in this chapter, we're going to see that it's a little bit more detailed than that. Not all exothermic reactions are product-favored. Overall, they are, all right? But not all the time. And that's what we'll be exploring in this section. Non-spontaneous reactions will require energy in order for them to transform from reactants to products, all right? So non-spontaneous, imagine in Chem 223 terms, would be more like a reactant-favored system. They're not as likely to occur. K's will be less than 1, stuff like that. And remember as well that in the back of your head, all reactions, whether they're exo or endothermic, require an activation energy to take place. And without that activation energy, no reactants will go to products. So the lower the energy of activation, the more likely the reaction is to occur, etc., etc. Spontaneity, once again, does not imply anything about time. Spontaneity sounds like it's like instant. It's going to happen right now. I flap my fingers. No. It's not. Spontaneity is not something in the domain of kinetics, which is where time is studied. All right. Spontaneity can be for a fast reaction and it can be for a slow reaction. Spontaneity just means, again, that it's product favored and the reaction should occur. The first law of thermodynamics does not predict if a reaction is spontaneous, all right? It doesn't say anything about how fast or slow a reaction is going to occur. But the first law does apply to all systems, all right? It doesn't matter if you're having a diamond turning into graphite or if you're using sodium and water, whatever. First law applies to all systems. And that applies to us as human beings as well. If you eat food, that's an energy transference. All the first law stuff applies. Pretty interesting. The philosophical connotations of this chapter are pretty high, and I'll try and point them out as we go through the lecture. So a process that's spontaneous is often non-spontaneous in the reverse direction. So let's think about an example. Let's say I have an iron nail, which is listed in that little picture right there. And I leave it out overnight and it rains and stuff like that. And the next day I come over and man, my iron nail is rusted. All right. Iron turns into iron 3 oxide pretty readily. So this would be an example of rusting. And that happened by itself, all right? No outside intervention or ultraviolet rays from the sun or anything weird like that happens. It happens by itself. That would be considered a spontaneous reaction. It is not likely that the rusty nail, if left out by itself, will instantly turn back to the iron nail it was before. That is a non-spontaneous reaction. It might be possible for us to turn that rusty nail back to a regular nail, but we'd have to intercede. We'd have to add energy somehow, heat, chemicals, whatever, all right? So processes that are spontaneous in one way will usually be non-spontaneous in the opposite way. Diamond, again, is something that is thermodynamically favored to convert into graphite, but it doesn't have to instill panic in you if you have diamonds or anything like that. It takes so long, all right? And so for diamonds to go to graphite, man, it's going to take generations upon generations and generations. So no one needs to go and sell their diamonds, I promise. It's a very slow process kinetically. Thermodynamics gives it the thumbs up. Like it's going to happen. But kinetics says, whoa, let's slow it down here a little bit. That takes a while. Now, on the other hand, in the lower picture, there's a burning piece of paper. If you very easily just have a little bit of spark added to it, an energy of activation barrier overcomer, if you will, man, that paper goes up like crazy. So paper burning happens by itself, basically, add a little bit of a spark, and it goes into the ash kind of thing. So thermodynamics says, yes, that's going to happen. That's going to be spontaneous. This reaction is also kinetically favored, i.e. it happens in our lifetime, our frame of reference of time. So both of those reactions, diamond to graphite and the paper burning, both of them would be considered spontaneous, i.e. thermodynamics says, go for it. But kinetics says, whoa, slow down there, Haas. On the first one, diamonds don't go to graphite easily. It takes thousands of years. On the other hand, kinetics is totally fine having the piece of paper burn into ash. So notice here, both reactions are spontaneous. Spontaneity has nothing to do with time. It's all about thermodynamics. Some reactions are spontaneous at one temperature and non-spontaneous at other temperatures. So there's a temperature dependence on this idea of if a reaction will occur or not. And a great example of this is ice going to liquid water and back and forth, all right? If you have ice and you're at a temperature that's above the freezing point of water, of course the ice is going to melt. That's going to happen spontaneously. On the other hand, if you take your liquid water and you put it in a temperature less than 0 degrees under the freezing point, then yes, the liquid water will freeze. Now, if you're above 0 degrees Celsius, ice going to liquid, that would be spontaneous. It's going to happen. But if you're above 0 degrees Celsius, you would not expect the liquid water to go back to ice. So the spontaneity above 0 degrees is for ice, of course, to go to liquid water. If you're below 0 degrees, below the freezing point, then naturally liquid water will go to ice. And you wouldn't expect at a temperature under 0 degrees Celsius for the ice to go back to liquid water if you're under 0 degrees. So you can see there's a spontaneity aspect of temperature that we'll talk about in this chapter as well. And yes, that assumes, 1 atmosphere pressure and you don't have a solution or something like that. But for normal water, these are the kind of things. And it does exhibit how temperature does have a factor when it comes to spontaneity. Another thing we need to talk about here is when things are reversible and irreversible. In a reversible process, the system changes so that the system and surroundings can be put back to their original states by just reversing the process, all right? And in theory, in thermodynamics, it's possible in all things, but it's actually quite rare. So in theory, all right, if you want your rusty nail to go back to iron nail, it should be possible. It should be reversible, but it's difficult, all right? You'd have to add the right chemicals. You'd probably still scrape off the outside layer of the iron as it turns to rust, so you'd have the underside showing. Reversible processes are rare, all right? We'll talk about them like it's possible, and it is possible most of the time, but they're actually usually quite rare. So just if sometimes once you commit to a reaction, it will be more difficult to go back the other way. So for example, think about that burning piece of paper. If we wanted that back to the original form, good luck, Charlie, because wow, you probably had like writing on there, and getting it back just to the paper part would be hard enough, and then having the words on it would be difficult. So reversible processes are possible in thermodynamics, but they are rare. That'll be something else will come up here in a little bit. Irreversible processes cannot be undone by exactly reversing the change to the system. All right. And this is the more common kind of process. Now, usually, and I would say spontaneous processes are irreversible. So there's a nice car, you leave it outside for too long, it starts to rust. That'll be a spontaneous thing. That'll happen. The non-spontaneous reaction would be to have it go from the rusty car back to the original. And probably that's not going to happen. That's probably irreversible. So the non-spontaneous reaction, we could totally make it look more like it. And if you were an auto body person, you could probably fix it up so it looked that way. But chances of it going back, pretty difficult. So irreversible is definitely the hallmark of a spontaneous reaction. One way is reversible. The spontaneous way happens naturally, spontaneous, but the non-spontaneous way is usually considered irreversible. You might be able to get close and stuff, but it would be difficult. One thing that scientists studied a lot at the turn of the 20th century was the probability that a reaction would happen. Like, what factors go into making a reaction happen? All right, why? What makes for a spontaneous reaction? So the directionality of reactions is something that a lot of scientists have been really interested in. And people studied this quite a bit. They found that probability of a reaction being spontaneous, i.e. a reaction being product favored, is if the reaction had a dispersal, then it would be more likely to occur. Now, dispersal can mean basically two different things in chemistry. You can have a dispersal of energy, you can have a dispersal of matter, or you can have a dispersal of both energy and matter. So what that means is you have a concentrated energy source and or a concentrated matter source. And when after the reaction occurs, dispersal means that the energy has been dispersed, so it's no longer in a small area, it's more dispersed over a wide area. And the same thing for matter. You had a concentrated matter source, it's dispersed, and so everything is kind of spread out. If you can have both energy and matter being dispersed, then that's really good. Boltzmann, the guy there showing his headstone there on the right, was a person that really studied this a lot. And his equation up there, which we'll mention briefly, is given right here with the magic S, and we'll talk about that. The little k is the Boltzmann constant, and it's a constant that's used in physics a lot. We won't use it so much here, but that constant was named after him, so Boltzmann really took care of business.
Consider a pair of flasks, one containing gas molecules, the other completely empty. If the flasks are connected at their mouths, gas in the filled flask will move spontaneously to the empty flask by its molecular motions. Eventually, the distribution of molecules will be even throughout the flasks. The final state in which the matter is more dispersed is much more probable than the initial undispersed state.
So this is an example of a gas. You've got a tube right there with a connector, all right? And initially the connector's off. You have a vacuum on one side and you have a gas on the other. Well, if you open up that valve right there through effusion, if nothing else, which we talked about back in the gas laws, the gas will distribute, all right? It's going to disperse from the concentrated bulb on the left to kind of an even distribution over both bulbs when everything is done, all right? This is an example of matter dispersal. You're starting with a concentrated matter source, i.e. the gas is just on the left side. You open it up, the gas distributes evenly over both bulbs. So this would be in the probability of spontaneous reactions. This would be a very likely candidate for a reaction which is going to occur. You expect the molecules of gas on the left to distribute evenly on both the left and the right. This is an example of matter dispersal. And if you can have matter dispersal, concentrated matter going to more distributed matter, you have a higher likelihood of your reaction occurring, being spontaneous. So here's a question. Which process represents matter dispersal? Okay. Cleaning your messy room. Well, cleaning your room, all right, would mean taking matter, which is all over the place, i.e. the mess, and putting it in a more organized matter, i.e. putting it in closets or drawers or whatever. That's not helping matter dispersal. That's actually fighting matter dispersal, all right, because your matter was distributed and all the junk in your room. Now it's all nice and tidy. Cleaning your messy room is not helping matter dispersal. Now, condensing gaseous water. So if you condense, you're taking a gas and turning it into a liquid. Gases take up a lot more volume. They have lots of energy and stuff like that. Liquids are very dense. Like the density of liquids is greater than the density of gases. We talked about that in Chem 222. So that's not helping matter dispersal at all either. C is the same kind of thing. You're crystallizing a solid from a solution. So in the solution, you must have little solid particles running around in solvent. You're able to crystallize them, i.e. concentrate the solid into the crystal lattice, all right? That's certainly not matter dispersal. That's fighting matter dispersal. D, though, eating dinner. Now think about that. Now let's say you had a burrito, which is what I had a while ago, all right? A burrito's nice, compact little food source. You eat them up. Well, first of all, you have to chew it, break it into lots of pieces. Then in your bodies, the energy is distributed throughout your body. And of course, some of it comes out as waste and stuff like that. Guess what? Eating dinner is actually a great way to see that you've got matter dispersal. You're taking concentrated food sources, consuming it, making it go into energy, getting rid of it as waste and stuff like that. You are absolutely helping the spontaneity of that reaction. Dinner is meant to be eaten. Woohoo! So this is a silly example, but it does show how matter can be distributed in some strange ways. Now, the last one, you're taking ammonium dichromate, which is a compound, and you're forming it from water into and chromium 3 oxide. Notice you have all those different pieces going into ammonium dichromate. That's not matter dispersal either, all right? You're taking water into and the Cr2O3 to make the NH42 Cr2O7. Lots of pieces to one piece. That's not matter dispersal. That would be against it. But eating things is a great way to disperse matter, and human beings are great at distributing matter. We just go around, basically. We eat, we use fuel, we drink things and stuff like that. We're great at dispersing mass.
Stored chemical potential energy is released from reactant molecules in an exothermic reaction. This energy spreads out or disperses over the product molecules and the molecules in the surroundings.
In addition to matter dispersal, energy dispersal is another way that influences the probability of a reaction being spontaneous, i.e., if you have some random reaction and you want to know if it's going to occur or not, you want to see if there's going to be energy dispersal. Now, earlier I talked about how eating food was matter dispersal. Well, let's say that you eat a gummy bear, all right? Gummy bears are kind of one of my favorites right now. It's a long story. I'm such a dork. But anyway, I eat a gummy bear, tasty, tasty. But in my body, the energy of those sugar bonds is broken up and distributed so I can move my arms and think and do all those kind of things. There's an energy dispersal quality to eating as well, all right? Energy comes to our bodies from the foods we eat. So energy dispersal, eating gummy bears, is another way to tell if a reaction is spontaneous or not. It's not just about matter dispersal, it's also about energy dispersal. And we'll see examples of this chemically here. This is why exothermic reactions we considered up until this chapter to always be spontaneous, i.e. they would occur, because if you can get energy distributed from the inside to the outside, from the system to the surroundings, i.e. the temperature feels warm after the reaction occurs, wow, that's a great way to predict anyway that your reaction will be spontaneous and it's going to happen. Exothermic reactions, enthalpy, negative delta H's, all that stuff, they involve a release of stored energy. All right, it goes from the system that's being studied to the surroundings, and this is why we said that usually exothermic reactions are the ones that are going to happen. That potential energy in sugar or that potential energy in sodium when it reacts with water and stuff like that, it basically goes out into the outside. So it goes to the solvent, it'll go to the glass container, it'll go into our bodies, whatever kind of system you've got. And that final state when the energy is dispersed, so it goes from concentrated to a more dispersed state, that's a more probable condition that makes reaction much more likely to be product favored and spontaneous. But notice there it says usually. Energy dispersal is a big part. But remember, there's also matter dispersal. So there must be something else happening besides enthalpy. This reaction, which I'm just going to show real fast for, effect basically, is called the thermite reaction. It's a very exothermic reaction. It's very spontaneous. You do have to kind of activate it. You have to get over that energy of activation barrier. But boy, once it goes, thermite is really powerful. Thermite reaction is one way to make elemental iron. All right. It's interesting that people do that. You can see the amount of energy was released. They had a whole blast shield and all kinds of stuff up there. It's a very exothermic reaction. So they added just a little bit of glycerin in this case to kind of activate the reaction. And man, it takes off and you end up with a lot of energy. Thermite is sometimes used in movies as they're going to make a bomb or something like that. And they use thermite as an example of that. I don't know enough about explosives to know if that's legit or not, but it is kind of an interesting. And we can definitely say that, first of all, it's very exothermic. And because it's occurring, like you can see the bam part right there in the picture, that means it's also spontaneous.
In the center beaker is water at room temperature. To this we add solid ammonium nitrate. The ammonium nitrate dissolves. Usually, a reaction that occurs so readily is exothermic, but we see from the thermometer that this reaction is endothermic. The temperature of the water drops significantly. This reaction is not favored energetically, yet it still occurs.
Reactions that are exothermic, energies released, are certainly spontaneous. They definitely happen. And again, up till this chapter, we've always assumed that it was only exothermic reactions that are spontaneous, that occur. This is an example of a reaction which is nowhere near as cool, in my opinion anyway, as the thermite reaction. But what it's showing ammonium nitrate dissolving in water, all right? And woohoo! I know you're excited by that one. Wow, I can go take table salt and put it in water. Woohoo! Anyway, why this is cool for this discussion, all right, is that it dissolves, all right? And you're like, okay. Why it's interesting that it dissolves is it's an endothermic reaction. And you could actually see there the temperature decrease. It started off at 23 or something and went down there to 11.6 or so. So this is an endothermic reaction, but the stuff is dissolving, all right? And if it dissolves, that means it's spontaneous, okay? So this is an endothermic yet spontaneous reaction. And so obviously enthalpy is not enough here to understand why reactions are spontaneous. We need more than enthalpy to understand spontaneity, and that's what we're going to start looking into. So this reaction, again, not anywhere near as cool as thermite and, adding sodium to water, these kind of things. However, from an intellectual perspective, this is a fascinating reaction because it's endothermic, yet it's occurring. It's spontaneous, yet endothermic. So what we're going to do now is look at the rules used to explain really what spontaneity is all about. To understand why spontaneity is about more than enthalpy, we need to introduce entropy. And entropy is one of the most fascinating of all ideas in chemistry as far as I'm concerned. Now, we talked about how energy dispersal and mass dispersal kind of help make reactions spontaneous. Well, energy dispersal is related to enthalpy, all right? So exothermic would be energy dispersed and stuff like that. On the other hand, if you didn't have energy dispersed, it would be endothermic. Entropy is related to the mass dispersal part, and entropy is really a measure of disorder. It's a measure of randomness. If you have things that are very organized, you are not helping entropy. I always like to tell people that if you're a person that doesn't like to clean up your house or your room and stuff like that, hey, you're helping entropy. Woohoo! And that's really dumb. And, if your parents or whoever get mad at you for not cleaning your house, then please don't use thermodynamics as an excuse. However, spontaneity is related in its own way to entropy, to disorder, to messiness, all right? And there's a lot of philosophical implications that come out of entropy that aren't necessarily as obvious when it comes to enthalpy. So entropy is given the symbol S, capital S, and it is related to mass dispersal. So going from a very organized mass, concentrated mass, to a more distributed, i.e. messy and random state of matter. Entropy started with Boltzmann, and on his headstone back there, it said S equals K times the natural log of W. And W is the microstates of a system, and we'll talk about what that means in a little bit. And the number of microstates, the more places it can be, are related to the entropy. It's entropy equals the Boltzmann constant K times the natural log of the microstates. You don't need to use this equation because this isn't very helpful for us, but I wanted you to know where entropy originally came from. K is that Boltzmann constant. There's the actual number. No, you don't need to memorize it. We're not going to use this equation. However, what is important here, if you have fewer microstates, you'll have lower entropy. And if you have more microstates, you'll have higher entropy. So imagine if you have all of the pencils in your house in one drawer, all right? Well, you could have the pencil with the lead facing left or right. Those would be microstates, but there's probably not too many. On the other hand, if you take those pencils and you throw them around your room, oh man, now there's all kinds of these places, these ways that pencils could be. They could be, perpendicular perpendicular to where they were held before. They could be stuck in the ceiling. They could be in the garbage can. You could put them down the garbage disposal. I don't know. There'd be lots of different ways you could put those pencils in your room. And the ways that the pencils can be in your room is this microstates, which is really weird, I know. The more microstates, the more ways you can put the matter around, that means you're going to have more entropy. So what this is saying is that if you have an organized matter source, you're going to have lower entropy, fewer microstates they can be in. On the other hand, if you have lots of disorder, lots of possibilities for where the different pencils can be, then you're going to have higher entropy. All spontaneous endothermic processes have an increase in entropy. Entropy is enough to kick the reaction to the spontaneous level, even if it's endothermic. We're going to see that enthalpy and entropy sometimes kind of like fight for if a reaction is going to be spontaneous or not. Sometimes enthalpy and entropy both want a reaction to be spontaneous, and sometimes they fight. And sometimes neither one of them wants a reaction to be spontaneous. So we're going to see here that enthalpy and entropy can work together, and they can work against each other. We'll talk about how to figure out when it does and when it doesn't. This is a reaction showing an atom A, two atoms A and B, and atoms A, B, and C. Okay, so bear with me. And in this different scenario, we've got a two-flask system. Now, focus with me just for a second on if you have just atom A. Well, if there's two flasks, atom A could be on the left side, or atom A could be in the right side. So that would be like two microstates, all right? And they take the number of microstates and they raise it to the number of atoms to figure out. So in the first case there, with just one atom in a closed thing, you'd have two states. On the other hand, if you have two atoms, A and B, then there's four possible microstates, all right? So you can see A and B could both be on the left, A and B could both be on the right. You could have A on the left, B on the right, or you could have B on the left, A on the right, four microstates. And then it gets more complicated. So you can see that three atoms has a lot more states. You can imagine that four would be even more. You basically take 2 to the number of atoms. So now imagine if you had 6 times 10 to the 23rd, 2 raised to that power. Goodness, that's a lot of different microstates. So entropy can get pretty crazy pretty quickly, all right? And again, we're not going to do that much with microstates, but I want you to see kind of what they're thinking. With pencils, I was arguing, you could have pencil on the ground, pencil on the table, pencil stuck in the ceiling. I don't know. Those would be microstates of pencils. This is a better chemical example that shows the possibilities. And again, this is just for two different like flasks, all right? If you had 3 flasks or 4 flasks, it would be crazier. Entropy can get pretty crazy. But when all is said and done, entropy is about disorder. And the more possible states you have, the higher disorder is possible.
Molecular motions are much more random in the gas state than in either the liquid or solid states. Motion in a liquid is more random than that of a solid. Gases tend to have the highest entropies, while solids have the lowest.
Entropy is actually a quantity that can be measured, all right? And I'm going to talk about here now some of the factors that affect the entropy values you might see. This is an example of water's entropy, but in 3 different phases. We're seeing water as a solid, which would be ice, of course, liquid water, and gaseous water. And those numbers there represent entropy values. So ice water would have an entropy of 47.91 joules per mole Kelvin, liquid water the 69 number, and gaseous water the 188. So notice here, and this is a trend you see all the time, solids always have less entropy than liquids, and liquids have less entropy than gases. Now solids are very locked in place. They don't have a lot of microstates possible, all right, because they're stuck next to each other. So solids have fewer microstates. Liquids, on the other hand, the connection between them isn't as strong as solids. Like solids had stronger intermolecular forces in Chem 222. Liquids do have an intermolecular force, but it has a lot more flexibility. And flexibility allows for more microstates, more places for them to move around. Liquids have higher entropy than solids, but gases have no intermolecular forces on them at all to appreciate any reasonable sense. Gases can go all over the place. So gases have tons of microstates they can be in. Gases have the most entropy. So again, solids always have less entropy than liquids. Liquids have less entropy than gases. And we'll talk about those numbers here more coming up. Only pure elements in perfectly formed crystals at 0 Kelvin have 0 entropy, all right? And this is the third law of thermodynamics. And what it's saying is that basically, in a nutshell, you're never going to have 0 entropy. You're always going to have a positive entropy for a substance. Unless you have that pure elemental crystal at 0 Kelvin, which has so many problems with it, you can probably imagine it's going to be crazy. That's the only time you could have 0 entropy. So basically, the third law says that all substances will have an entropy greater than 0. And you can see there that solids are closer to 0 than liquids. Liquids are higher, gases are higher. So the individual entropies of substances will always be positive numbers, and that'll be important here coming up. There is an entropy guide if you're curious more about what's going on here. So here's a question. Which of the following will have the highest entropy at 25 degrees Celsius? Okay, well, there's a whole bunch of different things there. Notice here, though, what's important is that you have solids, liquids, gases, and unobtainium, by the way, is the false element they were looking for in the Avatar movie, the movie Avatar, when they're on that kind of jungle world, not the TV series. But anyway, I digress. Unobtainium's just a joke, ignore it. Anyway, if we answer this problem, sorry, Prophet back on, whatever. To answer this question, there we go. What we want to do really is look at the phase of matter, because remember here that gases have more entropy than liquids, liquids have more entropy than solids. And good old xenon there, xenon is a gas. And usually the phase of matter is the most important thing to consider when talking about the entropy. Xenon gas has the highest entropy by far. Gases are always higher than liquids, liquids are always higher than solids, and unobtainium is just my poor excuse at a joke. So anyway, when it comes to highest entropy, gases will always be higher than liquids, liquids will be higher than solids. Here's just some examples. Bromine, it's normally a liquid, but it has appreciable vapor phase over it, which is like a gas phase. So we would say that liquid bromine has a lower entropy than gaseous bromine. On the right is an example of water as an ice. Obviously, that nice piece of ice compared to the liquid water, we would again say that solids have less entropy than liquids. I did forget to mention that little 0 mark over it, that means standard states. So you're talking about standard versions of things, not, like next to the sun or in a vacuum or something like that. You'd have 1 atmosphere of pressure, blah, blah, blah.
Heptane at 1500 Kelvin has significantly greater molecular motion than it does at 200 Kelvin. The substance has greater entropy at 1500 Kelvin than at 200 Kelvin.
Compounds, their entropy is affected by temperature. And if you look at the units of entropy, they're always joules per mole Kelvin. Entropy is absolutely affected by temperature. And so in this example, you have a heptane at a lower temperature and a higher temperature. And the lower temperature, you have lower entropy. Higher temperature, you have higher entropy. And that's very common for all substances. I like to think about this as if it's cold outside. Like if it's cold outside, I'll go out and I'll be, I won't feel quite as energetic, but I do go outside and yeah, it's nice weather and stuff like that. And then I'm more excited, more energetic. All right. Well, this applies to entropy as well. Entropy in this context, though, would be more about like vibrations. It's vibrating more. It's rotating around more, stuff like that. It's having more microstates, basically. You're making the matter do things that it would be easier at higher temperatures than it would be at lower temperatures.
In general, the more complex a molecule, the greater its entropy. We can see this trend by comparing 3 alkane molecules. The amount of motion for each molecule translates into entropy. The more motion overall, the greater the entropy.
As molecules get more complex either through number of atoms or just even molar mass, generally the entropy increases. So in that video, it compared methane to ethane to propane, three of the alkanes we talked about in organic chemistry in Chem 222, and you can see their entropy values are increasing. So as the number of as atoms in the molecule increases, the entropy increases. You have more ability for those little atoms to have microstates moving around and stuff like that. This also applies though to molar mass, and this is an example of a bunch of noble gases, and they're all gases, so they're all gas phase. But notice how the entropy increases, and that's mostly just a factor of them having more mass. And so the individual, you can think about individual electrons or protons are moving around. I mean, they're still all gases. They still have high entropy, but xenon has the highest entropy of all because it's the biggest, and helium would have the smallest one. So molecular complexity and molar mass are certainly related to increases in entropy as well. Entropy is really fascinating, especially when compared to enthalpy.
The entropy of a solid depends on the strength of the forces holding it together. The weaker the attractive forces, the greater the motion of the ions in the crystal lattice, and the greater the entropy.
In Chem 221 and Chem 222, we use Coulomb's law to justify why some atomic bonds were stronger and weaker, and we talked about the distance between ions. But the part that's important here is that we also saw that the number of charges on the cation and anion do affect the force connecting the two atoms together. And this has an effect when it comes to entropy. Now, if you look at MgO and NAF there, MgO has a positive 2, negative 2, all right? And that's like two handshakes holding on to each other, we talked about in the earlier classes, and those are stronger bonds, all right? It's harder to break up a positive 2, negative 2 than a positive 1, negative 1. So positive 2, negative 2 combinations of ions actually are stronger. They don't go around as much. They don't have as many microstates. So MgO has a lower entropy than NAF. And the rationale is that sodium fluoride, a positive 1, negative 1, is like a single handshake. And I said, hey, what's going on? I haven't seen you. And someone says, oh, no, break it up. Well, it's pretty easy to break up a single handshake. However, if you have a double handshake, I haven't seen you forever. Well, someone wants to break that up. It's harder, okay? Entropy doesn't do as well when the forces between the ions get stronger. So you can see positive 2, negative 2, smaller entropy, not as much flexibility, not as many microstates possible. If you had a positive 3, negative 3, for example, aluminum nitride, ALN, that should have an even lower entropy probably than positive 2, negative 2 MgO. So all of these things are affected when it comes to entropy considerations.
When potassium permanganate dissolves, its crystal lattice is broken apart, leading to an increase in disorder, and therefore an increase in entropy.
Usually, and notice my emphasis there on usually when you put a solid in a liquid in a solvent to make a solution, usually the entropy increases, all right? Because you are taking that nice concentrated ionic lattice, putting it into a pure solvent, making a bunch of ion dipole forces inside, breaking up things. So usually entropy gets bigger. This is the weakest of all these assumptions though, and we're going to see in lab some exceptions to this rule, I'm letting you know. But overall, if you have to guess, making a solution will increase the entropy relative to the pure substances. Which of the following would represent an increase in entropy? Okay, first of all, freezing of water. So taking liquid water and turning it into a solid. That would not be an increase in entropy because liquids have higher entropy than solids, which is what you're turning it into. So that wouldn't be a good example. On the other hand, if you take boiling water, liquid water turned into gaseous water, hey, that's a change of entropy. Liquids going to gas, that is an increase of entropy. Gases always have more entropy than liquids. I would say the answer B is correct. Now, let's look at C and D real fast. C, crystallizing a salt. All right, well, if you're crystallizing a salt from a solution, then the solution, you had all the ions running around, and making a crystal, everything is nice and ordered. That's not going to increase entropy. And D is also worth commenting on. You have 2 molecules of NO going to 1 molecule of N2O2. 2 molecules to 1 molecule, that's becoming more ordered. And you can think about that as like cleaning up your room. 2 pieces to 1 piece, matter was being distributed and dispersed, and now it's very concentrated. That's also not going to be entropy favored. It's not going to be an increase in entropy. In this problem, we're talking about increases in entropy when a change occurs, a change in entropy. And that's kind of a fascinating thing we're going to start getting into. But I want you to start thinking about factors that will affect an increase or decrease in entropy as the system changes. Here's a table of standard molar enthalpy values, all right? And they're just numbers. They should be all positive numbers. Every table has variance, so sometimes if you look at something up on Google, it'll be different than the one we use. At the end of problem set 5, I'm pretty sure, or online, I have a table of thermodynamic values. It includes enthalpy, which we used in Chem 221, but it does also include entropy, which we're going to use here. So you can look these numbers up and start using them. But anyway, entropy values always positive. Remember, only 0 Kelvin is that perfect crystal at 0 Kelvin, which never happens, so you can't have 0 entropy. There's some low entropy values. Notice that diamond is lower than graphite because diamond is more compact and hard to break up, but they should all be positive numbers. Let's talk a little bit more about some of the things from Chem 221 and Chem 222 that will help us in the next section, all right? And the first thing I want to do is talk about when you had an enthalpy change or a heat change Q, when you had a energy change for a temperature change, but no change in phase. If you remember from Chem 221, one of the equations we looked at was Q equals mc delta T. And remember that Q at constant pressure is delta H, so if you want to think about it as delta H, that's fine. But anyway, mc delta T is when you have a temperature change, but no change in phase. And change in phase means you have just a solid, or just a liquid, or just a gas. But you're not turning liquids to gas or anything like that. In Chem 221, we talked a lot about 4.184. That's the heat capacity of liquid water. That would be a cool number we'll use a little bit here. But anyway, if you have a temperature change but no change in phase, use Q equals mc delta T or delta H equals mc delta T. Now, if you do change the phase, if you turn your liquid into a gas, or you take your solid and you turn it into a gas, which is possible, then you have mass times heat of something. And that's what I called it. And it's very embarrassing. But the problem with phase changes is that the units are all over the place. The heat of something will have a name like the heat of fusion, heat of vaporization, all these kind of things. And heats of vaporization, heats of fusion, et cetera, they come in different units. So 333 joules per gram, that's the heat of fusion, and 40.7 kilojoules per mole is the heat of vaporization. Those are things for water, by the way. But notice that one is joules per gram and the other one is kilojoules per mole. So when you're doing an enthalpy calculation, the mass in quotes has to take into account whatever the heat value is given. So if you were using 333 joules per gram, your mass would be grams. On the other hand, you're using 40.7 kilojoules per mole, then your mass would have to be in moles in order to get them canceled out. If you have a phase change, there is no change in temperature, but if you change the temperature, you're not changing the phase. And again, this is something we did in Chem 221 back in chapter 5. We also did this in Chem 222 when we talked about the transitions between solids and liquids and gases, phase diagrams, stuff like that. So if this is looking a little unclear, absolutely go back and review. This was a diagram we used in Chem 222, I believe. It shows the transition of taking ice at minus 50 degrees on the y-axis here, and you're turning it essentially into steam. You could go up to 200 degrees or whatever you want. So notice here there's like some parts with a slope. So like this part right here, that's taking the ice from negative 50 to 0. And that would be some type of MC delta T transition. On the other hand, then there's this kind of flat part right here. And you can see on the y-axis, or excuse me, the x-axis, it's a heat and energy axis. If you're melting something, that's a phase change. You're turning the solid, in this case, into a liquid. It's going to take so much energy, but there's no change in temperature, i.e. the y-axis is constant. Then you can take your liquid at 0 degrees and you can heat it to a liquid at 100 degrees. That part right there, that would be an MC delta T transition. You're not changing the liquid water into solid water or gas or anything like that, but you are heating it up. Then there's another flat part right here, and this is when you're turning the phase of liquid into a phase of gas. That's a delta H times M, or a heat of something times mass of something. And then once it is a gas, you would have another MC delta T right here for steam as you heated it from, say, 100 degrees to 200 degrees. Anytime you go from a lower temperature to a higher temperature, it takes energy. It's endothermic. On the other hand, if you go from a higher temperature to a lower temperature, it's exothermic. You're going to get that energy out. So these are the kind of things we talked about in past classes, and they will help you out in the material coming up here soon. MC delta T was what scientists use for figuring out the enthalpy of a transition where there's no change in phase, but you are changing the temperature. Well, for entropy, the corresponding equation is delta S equals NC times the natural log T2 over T1. Oh boy. N is often the symbol for moles, and that's what it is here. So in this version of the entropy equation, you want to turn your mass into moles. C is what they call the molar heat capacity. So it would be so many joules per mole Kelvin, all right? And then T2 and T1 are Kelvin temperatures, like always. Now again, this is equivalent in enthalpy. In enthalpy, delta H, or Q, was MC delta T. This is the equivalent expression for entropy. So if you had a temperature change and you needed to figure out the entropy of it, you'd use NC natural log T2 over T1. Here's just an example. If you want to go through this on your own, you can, or you can just take my word for it. Either way is fine. Let's say you had 0.499 moles of water and you heated it from 281 to 294 Kelvin, and you wanted to find the entropy change for it. Okay, well, 0.499 is the moles. T2 would be 294, the final temperature. T1 would be 281, and we do need the molar heat capacity. So the 4.184 number we talked about in Chem 221 is joules per gram Kelvin. We need to turn our joules per gram Kelvin into moles, and it's not too hard. Grams and Kelvin are in the bottom and joules are in the top. So in order to turn it from a grams heat capacity to molar heat capacity, we essentially have to multiply by the molar mass. So 75.40 is the molar heat capacity of water. And we've never used it because we don't usually do molar heat capacities, at least in the earlier classes. But for this problem, that's what you need. So once you have that number, take the moles, multiply it by the molar heat capacity of water, natural log 294 divided by 281, entropy change 1.70 joules per Kelvin. Now, I want to talk here really fast about the difference between a delta S, which is what we're calculating, and an individual entropy S. A delta S is a change in entropy, all right? And a delta S that's positive means you have an increase in entropy. However, there's nothing that says you can't take the water at 294 Kelvin and turn it into water at 281 Kelvin. And if you did that, you'd end up reversing your T2 and T1, and your delta S would come out to be a negative number. A change in entropy can be positive or negative. In this case, you're increasing the temperature, and as increases in temperature occur, the entropy goes up as well. So the entropy is definitely increasing. But if you lowered the temperature, you would be decreasing the entropy, and you'd have a negative delta S. So delta S can be positive or negative. It's a change in entropy. The individual entropies of molecules will always be positive numbers. They are the values that have to be greater than 0. Only 0 is the perfect crystal at 0 Kelvin, which is basically make-believe. A change in entropy, though, can be positive or negative, and we'll start talking about how to interpret that. If you have a phase change and you want to calculate the entropy for it, entropy phase change values, delta S, equals Q over T. Q is the heat transferred in a phase change, and T is the Kelvin temperature. Now, delta H and Q, remember, are related. If your Q is transferred at constant pressure, then that's what equals delta H. So for this particular example, Q is 40,700 joules per mole. And this is, believe it or not, something we did in Chem 221. But just for right now, take it as a leap of faith.
When liquid water converts to the vapor state, its molecules disperse over a greater region of space. This represents an increase in entropy.
So when you calculate the entropy change for this phase change, you would take the Q, you would divide it by the temperature it happens, and figure that out. Now for this particular phase change, this is boiling of water, all right? And boiling of water happens at 373 Kelvin, 100 degrees Celsius, all right? So that's the temperature we're going to use. The 40.7 number, that's the heat of vaporization, and that's something we talked about in Chem 221. But if you look up that number, the heat of vaporization for liquid water going to gas, it's 40.7 kilojoules or 40,700 joules per mole Kelvin. So take that number, divide by the Kelvin temperature, and you're good to go. Now, a phase change in entropy would be equivalent to the delta H expression for a phase change. And again, like we talked about earlier, that's the mass of something times the heat of something. So heat of vaporization would be the 40.7 joules per mole value. You'd multiply that by the mass in order to find the enthalpy. The enthalpy change would be the mass times the heat of that. This is the equivalent. So if you wanted to find the entropy change for a phase change, use Q over T. Let's calculate the change in entropy for the vaporization of xenon at its boiling point of minus 107 degrees Celsius, which is 166 Kelvin. Remember, to go from Celsius to Kelvin, you add 273.15. And it's given the fact that delta H vaporization, the heat of vaporization, hint, hint, 12.6 kilojoules per mole. Okay, so to figure out the entropy change for a vaporization, for a phase change, i.e. going from liquid to gaseous xenon, delta S equals Q over T. And like we saw in the last example there with water, the Q part is related to the delta H of whatever transition you're going through. So we want to vaporize liquid xenon to a gas phase. Q is going to be this delta H vap. Now, the answers there are all in joules. So let's take 12.6 kilojoules per mole and multiply it by 1,000 to get joules per mole. And we'll divide that then by the Kelvin temperature, which is that 166 number. Anyway, you do all this, which is really exciting, I'm sure. 75.9 joules per mole Kelvin is the entropy change for the vaporization, for turning liquid xenon into gaseous xenon. This would be equivalent, once again, for finding the delta H for a phase change here. In that case, we would take the mass of xenon and multiply it by the heat of vaporization for xenon. You can do elaborate phase diagrams for entropy, just like you could do for enthalpy. And earlier we saw the version with enthalpy. In this version, we have entropy on the y-axis and temperature on the x-axis. And you can see how there's different parts. If you're just heating a liquid, that's when you use that NC, natural log T2 over T1 thing. That would be for heating the liquid, heating the vapor, and down here you'd have heating the solid. If you have a phase change, which is melting and evaporation on this particular one, that's when you'd use the heat divided by the temperature part, and you can see how there's quite a bit of entropy involved upon going from, say, a liquid to a gas. Gases have more entropy than liquids. There's also, though, an entropy change going from a solid to a liquid. Liquids have more entropy than solids. So there's all kinds of fun things you can do with entropy, just like we did with enthalpy. Oh, joy.